to really apologize. I had to move out of my house for a while, and I left the midterms there, so I'll bring them Thursday. And people did well, so for the most part. So I'll turn those back to you next class. And then I guess you'll be meeting with Noel this week in lab, discuss your projects, having a few come visit me, which is great, and talking a little bit more as time goes on. Any other scheduling things I should mention I can think of?
Yeah, just the lab will be on Zoom.
Yeah, your lab's on Zoom,
So you don't have to come in.
and it's scheduled, I think.
Yeah.
It's slots,
Yeah, it's
right?
slots of like 7 minutes, so you can just log into one of those. Yeah, I think that's it.
And then I'll move it on the greeting page on B courses, but I'm gonna move my office hours to those 15-minute slots because it seems to be doing better. So you could schedule specific slots, either come into my office or not on Tuesday mornings. If that doesn't work, let me know and you still wanna meet, I can find another time. Okay, any questions, anything else before I start? All right, so we were here last time, we're talking about logistic regression version of mixed model. And I was just starting to go over the simulation. And again, I'm simulating data that comes from, a model that looks like is 1 over 1 plus e to the minus. Okay, so I could either write this as an expectation or just a probability y. ij equals 1. So probability of some event is a function of covariates and then this random intercept. And that has to come from some distribution. And I'm generating just like the model assumes it's going to be, so beta 0. I is normal, 0. And I use 3. So mean 0, always have mean 0, and standard deviation 3. And so anyway, I just make a data set, which I showed you last time, which it assigns, first of all, that makes the number of people. It assigns them each their own intercept as a random draw. That's what the model implies, that you're taking a random group of people that have a random intercept. Beta is 0 plus beta 0I, and that comes from a normal distribution. And then, of course, I have the x. And again, I did it like it's a fixed design, so everybody goes 1 to 10. Of course, we often see data that's not like this at all, but. Okay. Hold on 1 sec. Okay, I'm just going to get out 1 sec. That as well. We typically just see the x, the y, the ID, and the time. And again, just so you realize, so the intercept, according to this model, applies to all observations on the same subject. It's a model, right? So it may be true, may not be true in practice. So then we just looked at comparing, let's just fit a random intercept model. This is the true model here, right? So I have a x, so beta 1x plus a random intercept, so beta 0 plus beta 0I, family, of course, binomial, because the outcome's binary, so it's a logistic form to the regression. And we get, our estimate of the coefficient. So again, this is, beta 1 hat, and according to the model. And then I'm just using, just to remind you, this is what the little function you have access to that does like lincom for mixed models. So I'm doing that, and I'm getting I want the odds ratio, and I get 7.9. So pretty big odds ratio, right, for a unit change in X. Did I do unit change? No, I did 5 unit. That's for 5 unit change. So And again, if I just wrote this out to get just to solidify what the interpretation of that odds ratio is, that's like the logit of Pyij given xi little x plus 5 and beta 0I minus the same thing. Except for xij is now just little x and beta 0I. And that's going to be equal to beta 0 plus beta 0 I plus beta 1 x plus 5 minus beta 0 plus beta 0 I plus beta 1 x, which is going to be 5 times beta 1. So that's the log odds ratio. The difference of two logits is the difference of log odds, which is log odds ratio. So anyway, notice the one thing is I only got this up alone because I assume that this was the same, meaning this is an within person odds ratio. I'm keeping the person fixed at beta 0I. Doesn't matter what beta 0I, but if I compare two people with two different people, I'm going to have a beta 0I and a beta 0I prime in this equation. So it only cancels out if I keep it fixed, which means it has this interpretation that it's the within subject odds ratio. What happens if I keep a subject fixed and increase their x by 5 units? Does everyone see that? So when I compare it to the marginal case, which is the GE, now I will point out that these models are not compatible. If you have a logistic regression model, random effects model, it doesn't mean that your marginal model is going to be logistic as well. So in fact, it won't be, but it's a reasonable approximation. So we'll just assume, so this model again it's different. There's no conditioning on beta 0I, right? It's plus 1 plus e to the minus. And I'll put stars here because they're not the same meaning anymore. So that's that model, right? I'm not conditioning on the subject. It's like I take a random sample of observations and I'm just getting the odds ratio, ignoring which which observation comes from which person. And you can see here, same data, that I'll just do the same odds ratio is 2.9. So it's quite a bit less. And this one, again, this interpretation is if essentially I can write and this just means it's the average probability, right? Can be basically just say the average of P Yij equals 1 given Xij beta 0I, where I'm averaging with respect to the beta 0I, right? So these things are equal. Same thing. So it's the average probability. And of course, you're averaging this thing that's very nonlinear. So it has unexpected, it's not like a linear case where you're averaging linear things. It's just the average of linear things is just the linear sum of the averages of the x's, let's say, in the beta 1. So it's not the same thing because this thing is a nonlinear function. And because of that, these two quantities are not, they're not going to be the same. That is, the odds ratio in this model here, the marginal model, this one, is not equal to the one that's the conditional model, where you're conditioning on being the same person. In fact, they have a relationship, and you can see it in this plot here. So here's just the same same data generating distribution. I take a random set of people with their beta 0I and draw their curves as x increases. So this is you can see it's not linear, right? It's logistic. It starts low. For people that start low, you have the bounded 1 there, so it kind of compresses those up there. And here, this is the marginal curve. So these ones here are ij equals 1, given xij equals x, and beta 0I. This is what the one where beta 0I equals 0. So that's the curve of the average person, right? The average person, by definition, has beta 0I equal to 0. So I take the average intercept at 0. Well, it's beta 0 is the average. So this is, and so the average beta 0I is 0. Beta 0, it's the average of beta 0 plus beta 0 I is just equal to beta 0. Right, so the average intercept is beta 0 because this just averages to 0. And you can see this explains, I have to tell you what this curve is. This is the marginal curve. So this is yij given xij is equal to x equals 1 given that. So that's what the red curve is. It basically takes all these points, averages them, puts it there, all the points of 2, averages all these curves here. And you can see because this nonlinear pattern, the slope is much less for the marginal, that's the marginal one where you're margining over, you're averaging out all of the subjects' values for their probability to get the population average one, which is what GE estimates. It's always shallower. There is a relationship between these two models. So if I have a random intercept model versus a marginal model, the slope, that is the change in the probability for a change in x, will always be shallower because of this nonlinear relationship than the individual curves of subjects. And so you can think of this, this is the curve for the average person. This is the curve of the average probabilities. You're averaging over different things, and that nonlinearity creates the situation. So you can see, when you're low, these things kind of pull you down, and when you're high, these things pull you up a little bit. Pull you this way, that other direction. Your high ones pull you this way, and this pull you down relative to the average curve, and you get this shallower thing. This is just on the logit scale. It's easier to see on the non-logit scale. And that's due to what's called Jensen's inequality. Which means this one here is the expectation of the probabilities, and this is the probability at the average. So this is the average probabilities, is the red, and the black is the probability of the average person. And you can show that the steepness will always be highest for when you're looking at the probability for the average person, not the average probability across people. And that's just explicitly Jensen's inequality. So you get this phenomenon when you look at logistic. You don't get linear. In linear, they're the same. Whether I'm talking about how the, let's say I'm modeling some continuous outcome, how the outcome goes up with increasing x is the same whether I condition on the person or not. Because, of course, it's at the linear scale. And things cancel out nicely. We don't have that integral of that thing that's not average. I can show that explicitly too. So if my model is y, and xij is equal to x, and beta 0 plus beta 0I plus beta 1x. Well, if I want to look at the average one of these, I just average. Oops, I'm sorry. I have to redo this. So if I condition on the beta 0I, the person's random intercept, this is the formula. If I want the average of those means across all people, across all beta 0I, it's easy to show that it just equals this. Same betas. So in other words, I can define this as the change in the mean for a change in x of one unit, keeping beta 0I fixed, or when I compare two groups where I've averaged over the beta 0I. It's the same because of the linear formula. So it both have, beta 1 has both this marginal and it has an individual level interpretation of the effect. Well, that's not true of logistic. They're not equal. In fact, they're not equal in a particular way where the line is always shallower, which means when you compare the odds ratios are going to be in magnitude less, right? When I that to here, I would compare those two, I get an odds ratio. That's always going to be a smaller number in magnitude because if I'm going up, it means the odds ratio is greater than if the curve goes up, so the x increases the probability, then it's always going to be smaller in the marginal than the conditional. And if I'm going down, it'll also be smaller down, right? So it means the basically this is the GE, this is the random FX. And that's a relationship you hear a lot when I talk about logistic regression. Some people make a lot about this. You can't independently estimate a within subject odds ratio unless that you have a time-dependent covariate, right? If it doesn't change, how do I look at the odds ratio that happens within a person? So you can still estimate it though, because you're not estimating a random coefficient, it's just a random intercept, but you only get the information about this difference just from the math. There's nothing independently that tells you. There's nothing in the data when you have a fixed, for instance, if we're looking at subjects and you have a fixed covariate, you can estimate the within subject odds ratio, but it's only a function of this model you're assuming. There's no independent information you have outside of the model. Something like where you're going to have lots of, this is obviously huge variability in where they start at. In our case, Rx is binary. In this case, it's 1 to 10, but kind of where you expect them to be. The variability of that baseline probability, let's say x is 0 in this case. So you'll often see this, and I mean, I'm not sure it happens much anymore, but when I taught social epi, in social epi, people will make a lot of the within community effect, because now they have cluster data. It's not typically longitudinal. We have communities. And you use a random effects logistic regression model and you get the within community impact. But since if you're measuring something that's constant for the community, you don't really have any information about that. You're just basically estimating, getting all the information about that within effect from assuming normality of the random effect in this particular nonlinear model. Any questions about that part? Turns out Poisson is like linear. Poisson will have that same property that linear does, that the marginal and the conditional, when you're conditioning on fixed random effects being fixed, they also are the same numbers, but logistic is different from those two. Okay, so let's just look at how it works in practice. I have a few examples here. So let's look at the data set we've been looking at. Again, the outcome is self-reported sexual activity, and the explanatory variable is drug or alcohol use. And we'll start by fitting, again, repeated measures, and we'll start by fitting a simple random intercept model. Now in this case, we actually could get the within subject odds ratio directly. For every subject, if I have days where they report drug and alcohol use and ones that they don't, I could compare the odds when they do versus they don't and get an odds ratio. So I could actually estimate this directly from the data, but we'll do it by assuming this model. And again, we're always assuming this, so that's just a default. we don't really have, not learning in this course, other possible distributions for this. There is some work on that. I would say the most common one would be where you have a latent, where it's a latent class variable. You might have heard that. So in other words, I don't think there's an infinite number of groups I can define by a normal curve. I think there's 5, and that it can be one of 5 numbers, and they have a certain probability. So you can do other models, but they're not, not commonly as done in health. Education, they do the sort of latent class things. They have different goals sometimes. And therefore, just as I said, e to the beta 1 star in this case, it's just beta 1 in this model. E to the beta 1 is the odds ratio for reporting the outcome for the same subject if they report drug use versus not drug use. It's really drug or alcohol use versus no drug or alcohol use. So this is like the within subject. And again, it won't be the same as the marginal because of this nonlinearity. Oops. So again, I'm just going to do some basic statistics. I mean, this is the kind of thing you would do if you didn't take the course, and it's a good idea before you just jump right in. Is I can check things out here. Like I look at the proportion of people that have certain response rates. It's always a useful thing to do. So for only 5 people essentially call. 5 of the teenagers called every day they were supposed to. And 35, or about 31%, don't have very low compliance. So we saw this very unbalanced data, not uncommon in these kind of observational studies where the people call in less. That's always dangerous, but because whether they call in or not probably is a function of other things that are related to the outcome and maybe the exposure, and that could case cause a bias, which we've talked about before, where certain people are going to dominate the estimates, those would have lots of observations, like these people, but they may be very different types of people that aren't representative. And then just looking at the proportion of times they report the outcome in these groups, so we can see there is effect. So those that report calling in less tend to have a higher proportion of days of their days that they report having the outcomes, reporting sexual activity. And you can see the teenagers that call in the most have the lowest. So there's definitely a relationship here that you might be concerned about that could bias your data. Remember, we talked about wanting to sort of ameliorate this in GE. Do you remember what that was? Because we have a choice with GE, right, with the working correlation. And so one thing you could do, it maybe fit exchangeable, because it will tend to downweight these people. Their weight will go down, it'll upweight these people. Relatively speaking, if there's high correlation of observations on the same subject, so you get more like a balanced design, which is sort of what you want here, right? That would make the most sense. You don't want the fact that they're not calling in to impact the estimates. But and this is the same, but for the this is the alcohol drug use proportion. And again, you same pattern. So you tend to be high in both if you don't call in as much, and you tend to be low in both, even more so if you call a lot. And again, these people, they're both kind of in the same direction in terms of the estimate, but these people will contribute much more if you just weight every observation the same than these people. And these are somewhere in the middle. So anyway, always a useful thing to do when you're looking at unbalanced data to try to figure out what's going on with this group, and is there some informative monitoring? That is there things that are related to my relationship of interest that also relates to whether or not they have a full data set or not data. Okay, don't worry about this. I'm just have a little function that gives you the odds ratio. Obviously, you can find this online just with a package, but here is our our estimates here. So this is right now the estimate of just the 2x2 table. So this is the pooled analysis. So it's somewhat equivalent to GE, particularly with independence working correlation, right? Gives you an idea what GE's trying to measure in this case. It's just you get the average probability, really just the proportion of people that report an activity, of observations that report sexual activity among those days where they report drinking and drug use compared to the days that they don't, and then you compare those two numbers, right? That's essentially just pulling across all observations without respect to the person. And so that's going to be equivalent to doing logistic regression GE in this case. That's what I'm doing, yeah. Okay, here is the simple random effects model. Again, I just have a random intercept at the ID level. It's going to look like this. Again, we get this might be interesting here, and then we get an estimate of the variance of beta 0I. That's really not super interesting, but it's the variance of the really the baseline probability when they report no drug or alcohol use. It gives you an idea of how that varies across, and we saw that this one. And we get